Talking about the gold with the nitric and the hydrochloric acid. Now the nitric and hydrochloric acid, we call that what? Special mixture. A special mixture that dissolves gold, aka royal water. It's known as royal water. What's the name of it? Royal water. This reaction has a name. Reaction mixture has a name. Just ask him what the name is. Aqua that's it. Royal water. So we went through the list, correct? As we're going through the list, so gold is a reducing agent. H plus is an oxidizing agent alone. H plus with nitrate is an oxidizing agent. Chloride, what was chloride? Chloride is a reducing agent. Chloride is a chloride is a reducing agent. But if you've seen the chart, you know, if you've actually looked at the chart and read all the entries in the chart, you'd notice that chloride occurs in actually more than once, right? Multiple places. There's some things that occur on both sides of the chart, like water. You know, if you saw the chart, water occurs in multiple places. You know, so we figure those out. Same thing with chloride. In fact, chloride is a reducing agent, and so is this. This is chloride, but in this case, chloride and water react. In the previous one, it was just chloride. The aqueous chloride reacting. In this case, it's chloride and water. And that's on the lithium side, so that's a reducing agent. And I think this is where we stopped. Was this where we stopped yesterday? Yeah. So let's continue down the list here. We continue down the list. Oh, here's gold. Oh, gold occurs in multiple places. Can I use this gold here? This is gold as an oxidizing agent. This is Au3+. oxidizer. Can I call this an oxidizer as well because gold occurs on both sides? The answer is no, because this is not gold. What is that? That's gold 3 ion. Gold 3 ion and gold metal are two totally different things, right? I mean, it's the same element, but behavior is going to be totally different. And so we can't use this, nor can we use this one, gold 1. Yeah, those are the common charges of gold, gold 1 and gold 3, right? But, you know, I saw chloride somewhere else. Do you recall seeing chloride somewhere else? Yeah, here's chloride. But, you know, we have 4 chlorides here, but we also need gold. Do we have gold present? Yeah, we have chloride and gold. We have chloride and gold present. And so this combination is a reducing agent as well here. And then we know water. Water is an oxidizing agent and reducing agent. I already looked through the chart, and there are no more entries. This is like 4 or 5 pages long, so I'm not going to go through the whole thing. But next, what do we do? Is step 1, we inventory. Step 2, we find the oxidizers and reducers. In fact, we want to find the strongest. And so, which one is the strongest? Well, let's start with the oxidizer first. Which one's the strongest oxidizer? So, what's the strongest oxidizer on the chart? What is that? Yeah, fluorine. Fluorine's the strongest oxidizer, so we can start at fluorine and then work our way down. And the first one we hit is nitrate and H+, so nothing changed there. So our oxidizer should be nitrate and H+, is the strongest one present. What's the strongest reducer present? So we start at the strongest reducer, which is what? Lithium, and work our way up in this case. And the first reducer that we hit is chloride and gold. It's the strongest reducer present. So the strongest oxidizer present is nitric acid. The strongest reducer present is chloride and gold, or it doesn't have to be nitric acid, just nitrate and acid. But now what we're going to do is we're just going to write out the reactions. For the oxidizer, it's easy. We just write the reaction as written in the chart. So that's nitrate plus 4H plus 3 electrons gives us NO gas plus 2H2O liquids. So we just copy that. For the reducer, what we have to do is, since lithium occurs on the opposite side, we have to reverse the equation. And so we reverse the equation. You know, we start off with gold, because that's our reactant. And so if we start off with gold, then that means flip this equation around, wherever it was. And it's going to be gold plus 4 chlorides yields this, AuCl4 minus plus 3 electrons. AuCl4 minus, what's this species called? This is what we call a complex ion. It's a complex ion. What it is, you know, normally when you think about gold is 3 plus, and normally we should have 3 chlorides. And so we should form gold 3 chloride, right? And this is a very interesting species, because what happens is a 4th chloride comes in and attacks it. And oddly enough, the way these chlorides bond, these chlorides end up forming a covalently bonded molecule. We'd expect it to form like a salt lattice, like sodium chloride, but what we see is something like this, where the chlorines, or the chlorides, covalently bond to this. These bonds are called coordinate covalent bonds, because both bonding electrons come from chloride. Gold doesn't give any of the electrons. And so gold is a 3 plus, each chloride is a 1 minus, so this whole thing carries a net -1 charge here. And this has a name. Well, I told you the name yesterday. What was the name again? Or did I tell you the name? This is called tetrachloroaurate Roman numeral 3 ion. And, tetrachloroaurate 3 ion. What happens here is this. What happens is that gold 3 is not stable. And what we can do is, when we have something like gold 3, Au3 plus, Aq, how is gold 3 stabilized? This charge. Well, this ion stabilized in water by forming a hydration or a solvation sphere of water molecules, and it's going to be stabilized by ion dipole attractions, right? Those ion dipole attractions, are those actual bonds? No, those aren't actual bonds. Those are intermolecular forces. However, when we have these chloros here, the way that the gold 3 stabilizes, these chlorides actually bond to the gold. And we'll talk about this reaction because this is chapter 24. We'll talk about this reaction in a bit. But we'll form a complex like this, and this helps. It really helps stabilize the gold 3. Although it's yes, it's gold still in the +3 oxidation state. That's where this Roman numeral comes. This Roman numeral is the charge on the gold. Aurate is another, aurium is I think the Latin name for gold, right? And so aurate would be here. Now this +3 charge is stabilized, but +3 is a bit unusual for gold. What charge would you have expected for gold? Gold would have been expected to have what charge? 1. 1's the correct charge. We expected to have a +1 charge, like silver. Because if it had a +1 charge, it'd be D10. It'd have that filled D subshell. Gold 3 is D8. And oddly enough, the D8, we have to lose 2 D electrons, which is going to go from D10 to D8. Well, the D8 configuration is stabilized by this structure. This is called a square planar structure. And we can better understand this using bonding, quantum mechanics. And the application of quantum mechanics to this is called ligand field theory. We can simplify it and come up with an easier version of ligand field theory, which is a full quantum mechanical approach to it, but we can do something simpler, like a Coulombic approach, which is called crystal field theory. Crystal field theory is discussed in chapter 24, but we aren't going to cover all of chapter 24. We're going to save that for the end of the semester, and so we'll talk about that later. All right, and so what we have here is this scenario where we got the two half reactions. We add up the half reactions, but here 3 electrons consumed, 3 electrons produced. They cancel out nicely. We don't have to multiply by any factor again. And so the reaction here is going to be nitrate plus 4H plus gold plus 4 chlorides yields NO gas plus 2H2O liquid plus, what's the name of this? Can you name that for me? Maybe I should hide this. What's the name of that? Tetrachloroaurate, Roman numeral 3. Tetrachloroaurate. And so what that's going to do is it's going to help stabilize things, right? It's going to make more stable products. That's what we want. We want to form as stable of products as possible. And so if we add some chloride in there, that's going to be the key ingredient to that. I mean, if we didn't have any chloride here, can we form any tetrachloroaurate? No. If we didn't have any chloride here, we'd form gold 3 ion, which isn't going to be as stable. A gold 3 ion is too unstable to exist in water. But anyway, going back to this, because you know what happens with gold 3. Gold 3 is a powerful oxidizer. Gold 3 being a powerful oxidizer can actually oxidize water. It's up there. But let's see. Are we done here? What's the next step? Are we at the final step? This is it? No. The final step is to do what? Well, to simplify. Simplified it, and then after simplification, we do find the driving force. And so the driving force, the easiest way to do this is off the half reactions, is because of the conjugate relationship. If this is the oxidizing agent consumes electrons, then this must be its conjugate reducing agent. And if this is the reducing agent, which gives up electrons, then this must be the conjugate oxidizing agent. And so what we do is this. We're starting off with this oxidizing agent and this reducing agent, and we're going to this reducing agent and this oxidizing agent. And so we compare the strengths. Which side is stronger? Which side's weaker? And so we just consult the chart. What's a more powerful oxidizer? Nitrate and acid, or gold, the complex? Let's take a look. I don't know why I keep getting logged out. Here. Well, what's the strongest oxidizer on the chart? What's the strongest oxidizer on the chart? Fluorine. So we saw the fluorine work our way down. The first one we hit is gold 3. But do we have any gold 3? No. We'll just keep going down the chart. Yeah, we hit another gold 3 again. Weaker. And so as we work our way down the chart, then we hit tetrachloroaurate 3 right here. And tetrachloroaurate 3 is going to be stronger than nitrate in acid, or nitric acid. And so we see that this is stronger. Now, because of the conjugate relationship, if we got this correct, then it must be correct that this has got to be weaker and this has got to be stronger. It cannot be weak, strong, strong, weak. It has to be weak, weak, strong, strong, or strong, strong, weak, weak. Otherwise, the conjugate relationship, you got it wrong. And so here, this must be the case, and we can look it up right here. That means NO gas and water must be a stronger reducer than gold and chloride. Is that the case? Yeah, because this is going to be closer to the strongest reducer, which is, what is the strongest reducer? Lithium metal. Now, is fluorine the strongest oxidizer ever? The strongest oxidizer in the universe? No, it's not, but it's what's on our chart. The same thing with lithium. Lithium's not the strongest reducer. There's more powerful oxidizers, more powerful reducers, but I'm not going to worry about those. And so do we have driving force? Hey, yes, I do. I have driving force. I have gas formation. Is gas formation a driving force in redox? Why not? Why not? It's a driving force in metathesis. Why isn't gas formation a driving force in redox? Does somebody have an answer?
Oh, it's the driving force, like, forming water is a driving force, and forming gas is a driving force.
All right. Forming water is a driving force. A lot of people learn that. When you water formation is a driving force. But I'd like you to forget that. I'd like you to forget that and replace that with stronger to weaker acid, because sometimes when we form water, that's not the driving force. It just was a byproduct. And so we have to, but the driving force, the reason gas formation is not a driving force here, I mean, it will help the reaction, but it won't, because in metathesis reaction, does the oxidation state change? Did I talk about this, right, already? And the way you can remember these types of things is to kind of review it, daily, or, it's early in the semester, so you can review it daily. That way it's easy to remember. There's studies, I've read one study where they say, you forget 60% of the stuff you learned yesterday. And so, my memory's not that good, so I probably lose more than that. And so the only way I can remember these things is by repetition, by seeing it over and over again, and then I'll remember it. But anyway, the reason is because in metathesis, since the oxidation states don't change, we're just looking for little changes in energy. Little changes in energy would be precipitation. Let's say you precipitated out barium sulfate, do you have to worry about an explosion occurring when you precipitate out barium ions with sulfate ion? So you can get a nice white cloudy precipitate. Did you guys do that? Gravimetric analysis of sulfate, precipitate out barium sulfate. Did you worry about an explosion occurring when bariums sought out sulfates and they came together and they precipitated out to form a cloudy white suspension? Worry about an explosion? No. Hey, did you worry about an explosion when you took HCl, a strong acid, and titrated it with a strong base, sodium hydroxide? You take a strong acid and a strong base, you better not, did you worry, I better not mix sodium hydroxide with my HCl because that's potentially explosive because I got a strong acid and a strong base. Did you worry about that? No, yeah, some heat's generated, and a lot of heat can be generated. You can have a steam explosion possibly, but you wouldn't worry about a chemical explosion. But if you take an extremely weak oxidizer, like water, is water a very powerful oxidizer? No, not at all. You take an extremely weak oxidizer and mix it with a pretty powerful reducer, sodium metal. Do you have to worry about an explosion? Yeah. You have to worry about an explosion because the charge, the charge means it's totally different. The gold with a 0 charge is totally different with the gold with a +3 charge energetically. They're hugely different. And so in redox, those things are not so significant. Things like gas formation, precipitation. Yeah, they help, but they aren't that significant because the main kick in the energy is going to be from the charges, and the charges changing, right? You have to worry about explosions when we're dealing with redox, right? In fact, I was reading the news yesterday, and there's a chemical plant that's on the verge of exploding. Did you hear about that? In Houston. What happened was there's a chemical plant, and the refrigeration system got swamped with water. And the backup generators got swamped with water. And so there's a failure of the refrigeration system. And they said if they can't cool down their chemicals, it's going to explode. They predict in 5 or 6 days the whole plant's going to explode. And so, I was thinking about that. Well, what do they manufacture at that plant? Do you know what they manufacture? Peroxides. Yeah, what do you know about peroxides? Are peroxides stable? In fact, peroxide, you should remember peroxide was the number 3 what? was like, that wasn't the number one, it wasn't the number two, it was the number three on one chart. I saw that chart the other day, yesterday I think. It was the number three what on that chart? Oxidizer chart. Yeah, it's not very stable, and so they need something to cool down. You know, and cooling down helps because when you cool things down, it slows down the reactions. Right? Keeps it. In fact, you know, normally you probably don't store your hydrogen peroxide in the refrigerator, but we do. We have 30% hydrogen peroxide. We keep it in the refrigerator because we don't want it to decompose too fast, and so we just keep it there. You know, household hydrogen peroxide, it's only 2%, I think, but ours is 30%, and so it's a lot less stable. But anyway, go with that. And so here, yeah, sure, yeah, that's a gas, but what's much more important is the charges. A gold 0 versus a gold in the 3+, hugely different in terms of stability. Right? Gold 3+ is not so happy. Gold is happy. You know? That's why in nature you don't find compounds of gold, you just find gold, chunks of gold, or elements of flakes of gold, or whatever. It's more stable. But this is not gold 3. This is gold 3, you know, stabilized by having these chlorides bonded to it, and so maybe that's better. But is this a driving force here, going from weaker to stronger? No. In fact, we'd say that we want to go from stronger to weaker, not weaker to stronger, because strong means strongly reactive. Strong means it's a strong oxidizer, it's a strong reducer. It means it's unstable, it's highly reactive, it's high energy. Weak means it's unreactive. It means it's stable. So we're going from something stable to something unstable. That shouldn't happen. And so we call this an NR. NR means no reaction. NR, no reaction. But didn't I tell you that aqua regia dissolves water? Not water, dissolves what? Gold. Didn't I tell you aqua regia dissolves gold? In fact, let's see. Aqua regia in action here. Does anybody have any gold that I can demonstrate this on? No. Are you sure? Your fellow students.
This reaction produces toxic gases and uses corrosive acid. They should be performed individually with drugs. Greetings, others. In this video, we're going to dissolve a gold coin in acid. Here is the coin. It's a 1/20th troy ounce Canadian maple. Now we add 10 milliliters of concentrated 12 molar hydrochloric acid. By itself, the acid does not react with gold, so we add another 1 milliliter of concentrated 15 molar nitric acid. The mixture is gently heated to speed up the reaction. Eventually, the mixture will turn yellow and bubble as the gold starts dissolving. We showed in a previous video that gold will not dissolve in either hydrochloric acid or nitric acid alone. What's happening here is that the nitric acid is first oxidizing the surface of the gold. Then the chloride ions and hydrochloric acid reacts with the gold ions to form a complex ion that dissolves away into solution. The nitric acid then further oxidizes the surface and the process repeats. We showed in a previous video that gold will not dissolve in either hydrochloric acid or nitric acid alone.
All right, so this is what's happening. For sure, this is a combination of reactions, actually. For sure, the nitric acid won't, because gold 3 is a lot less stable. And so this is going from weaker to stronger, so this doesn't happen. But what can happen is a little bit can react. If a little bit reacts, we form a tiny bit of gold 3, because the collisions you can't stop, and sometimes the collisions are violent enough, but we form a little bit of gold 3. If a little bit of gold 3 forms, then what can happen is the chlorides can attack it.
The chloride ions and
And so the chlorides come in, and then they're going to help stabilize the gold 3 by forming the complex tetrachloroaurate ion here, aurate 3. And so you can see that the gold coin is dissolving. Eventually we can dissolve the whole coin. Fortunately, matter is neither created nor destroyed in chemical reactions. So once they dissolve this, then they can reconvert it back into gold. But is it going to be a shiny Canadian maple leaf like this? No, it's going to be just chunks of gold they're going to get. But they aren't going to lose any gold. So what? Wait a minute. Didn't I just say there's no reaction here? And then there's reaction here. So what's wrong? Did the method fail? Did this method fail? Because clearly this gold coin is dissolving. You can see it. Those bubbles are the bubbles of the gas that are forming here. The gold coin is dissolving. So I would double check it, but this is right. We're going from weaker to stronger. There should be no driving force for this. And so can somebody tell me what I'm missing? Heat, yeah, heat can change things because that can alter it as well. And so heat, and there's something else I'm missing.
Reaction happening in steps?
Well, the reaction is happening in steps, but we can combine it as a whole. And Hess's law tells us that whether it happens in steps or you combine it in whole, it's the same thing overall. It doesn't matter, what the net is. And so we combine those two reactions into this one. And chapter 17 will separate them. But in this chapter, we'll just do it because this is just redox here. There's something else I'm missing. The molarity. What was the molarity there? Yeah, 15 and 15. 15 molar and 15 molar. Different ratios. But, nonetheless, when they mix it together, it's going to be concentrated. They're using concentrated. My predictions are based on what molarity? 1 molar. We call 1 molar what? Standard condition. So if we do this under standard thermodynamic conditions, we don't expect reaction to occur. The only way I can get this to kick off is by going non-standard. If I go non-standard and kick up the concentrations, then I can get the reaction to go. Okay. But at what concentration will this reaction go? Is it going to be 15? What if I use 10 molar? Would 10 molar work? Would 6 molar work? At what concentration will it go? Can you tell me? Not really. And so what you do is you just mix it together and see what happens, right? You mix it and see what happens. And we could do it that way. It's just purely by observation. But it turns out we don't. We could calculate it. We could calculate it because what we're doing here is this type of analysis is just very qualitative. This is like the Chem 1A style analysis of chemical reactions. In Chem 1A, the reactions either went 100%. If they went 100%, then we can calculate the theoretical yield, the percent yield, limiting reagent, excess reagent, all that. We can do the stoichiometry, right? Or there was no reaction. If there's no reaction, then nothing happened. But what we're going to do in Chem 1B is we got something like this, at what point does a reaction occur? At what point? And the way we're going to figure that out is we're going to do chapter 13 style calculations. In chapter 13, we're going to put a number on the driving forces. So for example, there's no driving force here, but what is that number? Well, it's like a negative driving force, right? Well, how big of a negative driving force is that? Is that something we can overcome? And so in Chem 1B, the whole point of this is this. we're going to be looking at equilibrium systems. Equilibrium systems is a balance here. And the balance is like this. We're looking at a competition between the reactants and the products. Which side is stronger? Which side is going to win? It turns out if the reactants and products are comparable in strength, then there's going to be an even mixture, or more even mixture, because if it's comparable in strength, then you expect more of a 50-50 balance. Whereas if the products are much more stable, then we get a Chem 1A scenario where the reactants are consumed, the limiting reactant is consumed completely, and we form a theoretical yield of product, right? Or if the reactants are more favored, then there's very little reaction. Maybe there's no reaction, or maybe there's just a little bit. It depends on the difference. It depends on the driving force, which dictates the equilibrium or the balance between the reactants and the products. And so we're going to spend almost the entire semester talking about the equilibrium, the balance between reactants and products in Chem 1B. Chem 1B, the major topic is equilibrium. And what is the equilibrium? The equilibrium is between reactant and product. And what we want to do is we want to figure out, what is it? What is it? If there's no driving force, how bad is it? Can a little bit happen or nothing at all? That's what we want. And but before I do that, before we get into all the calculations, I want you to have a good feel for what happens under standard conditions. What happens under standard conditions, because that's going to, if we can kind of predict what should happen, and then do the calculation and see, the calculation kind of matches our prediction, then that gives us a way of checking our calculation, right, to make sure our thinking is correct or whatever else. And so what we're going to do is we're already going to have an idea before we do our calculations and be what should happen. Right here, my idea of what should happen is there should be no reaction. To what extent is that? And there might be a little bit of reaction or absolutely no reaction. That's what we want to figure out. In this case, it turns out there's a little bit of reaction. And so you better watch out, probably even under standard conditions, you don't want to put your gold coin in this because or your gold jewelry, because it'll probably lose a little bit. Okay. And so, so the point is this: that's what we're doing now. That's what we're focusing on. And what we have to keep in mind is, we're really restricting the conditions here. Okay, so I have some practice problems to work out here. I want to stop with this one here just for a second. We got some ethanol, some potassium permanganate, some hydrochloric acid. You can kind of already get a feel for what's going to happen. For example, potassium permanganate. What do you know about potassium permanganate as far as chemical properties go? You've seen permanganate before. Permanganate was in the top 5 of what? Not the top 5 of the reducing agents. It was in the top 5 of the oxidizing agents. It was in the top 5 of the oxidizing. So you got a strong oxidizer there, potassium permanganate. Hydrochloric acid. Hydrochloric acid is not much. It's just a mineral acid. You got H+. H+ is a medium, moderate strength oxidizer. So chloride is one of the worst reducers you can have because it's conjugate. What's a conjugate? If chloride is a reducer, what's his conjugate oxidizer? If chloride's a reducer, its conjugate oxidizer is chlorine. Is chlorine a strong oxidizer? Yes. And so chloride's very stable. If you think about it, do you worry about chloride, eating sodium chloride, table salt? Worry about that? Chloride's a reducer, but it's pretty unreactive. So this is an oxidizer, mild oxidizer. strong oxidizer. What's ethanol? Ethanol's not on the chart. It's not in the top 5 of anything, right? But it is. It should be in the top 5 because ethanol is very reactive. What do you think ethanol is? Well, first off, what is the formula for ethanol? How many carbons does ethanol have? Yeah. What's an alcohol? OH. And fill the rest with hydrogen. It's an alkane. There's no double bonds here. So this is ethanol. Ethanol, you know, we could call it C2H5OH. That's what the book uses, C2H5OH. What do you think about its redox properties? Ethanol's redox properties. Now, when we talk about redox properties, we think in terms of electron-rich, reducers, or electron-poor oxidizers. Eric, do you think it's a reducer? Why?
The left carbon's
Left carbon's pretty rich. All right. Well, that's because you know how to assign oxidation states based on structure. But does anybody else know how? Does anybody else know? Well, let me ask you this. Actually, I already know the answer. You probably did oxidation states based only on formula. Did anybody do oxidation states based on Lewis structure? Except for Eric and... Is that it? Okay. What's the oxidation state on the atoms here? Which one do we do first? Hydrogen, oxygen, or carbon? Which one goes first? No. Yeah, go back to the rules in chapter 3. The rules in chapter 3 say hydrogen goes first. And then oxygen. Yeah, oxygen goes second. And so this is +6, -2 is +4. This got to be -4. So we have 2 carbons at -4 total, which means each one must be a -2. The thing about doing oxidation states based on formula is what we get is the average oxidation state. And sometimes we don't want the average. When you have an average, let's say I tell you, the average oxygen-hydrogen bond is 436 kilojoules per mole. What's the weakest oxygen-hydrogen bond? What's the weak? The average cost for the 60-inch TV is $700. What's the cheapest one? What's the most expensive one? Do you have any idea what the range is based on an average? No, and so oftentimes we don't like averages. If we do the average, normally when we report averages in science, we report the average plus or minus lambda 95. You know what lambda 95 is? Yeah, Eric knows. This is a confidence interval. And so what we do is we say, okay, this is the average, but 95% of the individual measurements should fall within this range. You know, 95% of the individual. And so then we see, you know, what that average is based on. Right? And so we get a little bit of data rather than just the average. Well, the average carbon is -2. Well, does that mean some carbons are +4 and the others are -8? You know, or does that mean, what does it mean? You know, the average here. And so this is why we do oxidation states based on Lewis structure. But when we do Lewis structures, there are 3 ways of counting electrons. What are the 3 ways of counting electrons in Lewis structure? 1, the octet or the duet. 2, formal charge. And 3, oxidation state. And so when we count the octet, you know, here, this carbon, does it have an octet? Does the carbon have an octet? Yes, because when we count an octet, we look at the total number of electrons around carbon. And that's 2, 4, 6, 8 electrons around carbon. What's the formal charge on carbon? What's the formal charge on carbon? 0. How did you determine it's 0? Well, a lot of people tell me, the formal charge is the number of bonds minus this, minus that, divided by 2, right? But that doesn't really tell me, what is formal charge? A 0 formal charge means what? And so give me a one-sentence definition of formal charge. Or rather than telling me in terms of a mathematical equation, just explain to me how you're counting the electrons for formal charge. Well, let me just tell you. The formal charge is that it's the charge that results when we divide up the electrons in a structure, assuming that the bonds are 100% covalent. 100% covalent. So if 100% covalent means this, a carbon-carbon bond is naturally 100% covalent because one electron, if it's covalent, we share the electron. So one electron goes to this carbon, one electron. It's a 50-50 sharing arrangement. A carbon-hydrogen, well, that's not naturally 100% covalent, but it's close enough. But we'll just say it's 100% covalent. And so what we do is we assume the bonding is 100% covalent and then count the electrons. If we do that, how many electrons end up on carbon? Well, the number of electrons that end up on carbon, 1, 2, 3, 4, and the other electrons end up on the other atom because it's shared. It's 50-50, so 100% covalent, right? And so when we do that, it ends up with 4 electrons. Well, carbon's supposed to have how many electrons? Valent. 4. So this gets a formal charge of 0. Formal charges we circle. So that gets a formal charge of 0. That's a charge that would result if the bonding were 100% covalent. Oxidation state assumes 100% ionic bonding. And if it's 100% ionic, that means winner take all. And so if we're doing oxidation state, we divide up the electrons differently. And so oxidation state would be like this. Carbon versus hydrogen, who's going to be the winner? Carbon, why? Why would carbon win over hydrogen? It's more electronegative. So carbon's going to take all the electrons here. Carbon versus carbon, which carbon will win? The left carbon or the right carbon?
It's a tie.
It's a tie. Here, it's not winner take all. We have to end up in a tie. So now let's count the electrons. 1, 2, 3, 4, 5, 6, 7. Carbon ends up with 7 electrons. It's supposed to have 4. It has 3 extra electrons, giving it the net what charge? If it has 3 extra electrons, it's going to end up with a net -3 charge, and so therefore its oxidation state is -3. -3. What's the oxidation state on this carbon? It's -1. That's right. It's -1 because we just do the same thing. Carbon versus hydrogen, carbon wins. Carbon versus oxygen, who wins? Oxygen. Carbon versus hydrogen, carbon versus carbon. It's a tie. 1, 2, 3, 4, 5. 5 electrons means it has an extra 1. It's -1. So the average is -2, but the left carbon is -3. The right carbon is -1. The left carbon is more electron rich, more reactive than the right carbon. Now, the oxygen is what? Oxygen is going to take everything. And so it's going to end up with 8 electrons. It's going to have an oxidation state of -2. Hydrogen ends up with nothing. And gets an oxidation state of +1, all of them. And so oftentimes we'll do this, and we'll see that if I look at ethanol, what would you consider? Ethanol electron rich because of oxygen has a -2, or ethanol electron rich because look at these carbons? Or or ethanol is electron poor because look at these hydrogens. Which is it? Which of those three is it? Was it the first one? Ethanol is electron rich because of oxygen? Was it the second one? Electron is electron rich because of these carbons? Or the third one? Ethanol is electron poor because of these hydrogens? The second one. Ethanol is electron rich. In fact, ethanol is a very good fuel. Fuels are good reducers, and ethanol is an excellent fuel. Problem number 3 is advanced. Problem number 3 is advanced because ethanol is not on your chart. You know, you have to figure out what happens to ethanol when it's oxidized by potassium permanganate. You know, and it depends. You know, it depends on how the conditions. You know, you could have really vigorous conditions in which ethanol is vigorously oxidized, or it could be mild. For example, you know, potassium permanganate, you could use concentrated potassium permanganate, or you could use very dilute potassium permanganate. Are they going to yield the same thing? It's like you can combust things. You can combust things under vigorous conditions, or you can combust things under mild conditions. You don't want to combust things under mild conditions because if it's too mild, you're not going to oxidize it completely. You might form what? Carbon, soot. You might form carbon monoxide. Do you want to form much carbon monoxide? No, you don't. And so the same thing, this. You know, what are we going to oxidize ethanol to? Is it going to be mild? Or is it going to be vigorous? Well, it depends on the conditions. Well, in this case, we would use the chart, but the problem is ethanol does not occur on the chart. And so normally what we do is we just assume it's going to be vigorous. When we do these reactions, we assume, like when we do a combustion, do you write soot as a product in a combustion reaction usually? Do you usually write carbon monoxide? You know, methane plus oxygen yields carbon monoxide and water. No, you don't even want any carbon monoxide, right? It's poisonous. And so normally what we do is we try to do it vigorously to go to completion, but sometimes it doesn't because, you know, like this, when we did the aqua regia, it didn't work under standard conditions, right? And that's what we're doing under standard conditions. And so this is a bit more complicated. This involves either making an assumption or doing something else. And not only for the ethanol, but also for the potassium permanganate. Because ethanol can be combusted to different levels. You know in the body what happens to ethanol? Does ethanol go straight to CO2? When you consume ethanol, ethanol is the alcohol in alcoholic beverages. So if you consumed a little bit of ethanol, does it go straight to CO2 and you exhale it out? No. It goes through a whole cycle. Initially the ethanol is mildly oxidized. You know, it's oxidized to what? Acetic acid or something. Have you ever had wine? You know, Eric might have heard this because I told this in Chem 1A, I think. But did I tell you about the camping trip to Joshua Tree? All right. On a camping trip to Joshua Tree, went to the dollar store in the town of Yucca Valley, and I saw, wow, Santa Barbara wine. Santa Barbara wine, 99 cents a bottle. 99 cents, what a deal. Had to buy it, so I bought it. And we went back to the campsite and getting all excited. You know, this 99-cent bottle of Santa Barbara wine. Open it, first sip. Oh my God, vinegar. Spit it out, used it to put out the campfire. But basically, what happened was, now I see why it was so cheap. Because the ethanol got mildly oxidized to acetic acid. Okay, unfortunately. Well, you know, we don't know where it stops. So, you know, when we get situations like this, where we get a partial reaction, the same thing with permanganate. You know, permanganate doesn't go straight to manganese metal when it gains electrons. for example, it can go from permanganate to this, which is manganese in the +6, to manganese in the +4, to manganese in the +3, to manganese in the +2, to manganese. Now this is under acidic conditions. Under basic conditions, it could go to this. It goes from this purple to this green to this blue to this black to this brown to this pink to this metal. And so we could partially reduce the manganese in permanganate, or we could fully reduce it. Where do we stop? Well, that's very tricky to predict, and it's tough because all we're doing is we're using the chart method. Now, if you're going to do something a little more sophisticated, you would use these diagrams, potential diagrams, to figure out where it's going to stop, right? But potential diagrams are beyond the scope of our course, and so we aren't going to deal with potential diagrams here. Usually when we do something like this, what we do is something called skeleton redox. In skeleton redox, which is at the end of chapter 5, we do not predict the products. The products are given. And so the skeleton redox is, you know what, forget it. I don't want to try to predict it. I'm just going to mix it and see what happens. That's it. Mix it and see what happens. Just observe. And so here, we'll mix some ethanol and some permanganate and see what happens. Well, under these conditions, the ethanol didn't go all the way to CO2. The ethanol was just oxidized to acetate. This must be under basic conditions, because under basic conditions it's acetate, and under acidic conditions it would be acetic acid. But anyway, this is ethanol and permanganate, and the permanganate didn't get reduced all the way to manganese 2 plus cation or manganese metal. It only got reduced to this, manganese 4 oxide. That's it. And so that happens under these conditions, and these conditions are whatever you mix it. Maybe we try to make it more vigorous, maybe we up the concentration, maybe we do this. We can change the products depending on what we do. Now that's getting too complicated, and so normally what we do here is, well, if you're not given this product, then we're going to say we're going to burn the ethanol all the way to, Eric should know, to CO2. And so going back to this, I don't tell you what the ethanol gets burnt to. The ethanol in this case is going to go all the way to CO2. This is what I told the Chem 1A students to do. Take the ethanol to CO2, and therefore we can figure out that half reaction by using the skeleton method. Now, potassium permanganate, the permanganate in acid is already in the chart. The permanganate in acid, we just read off the chart. Permanganate in acid is going to go all the way to manganese 2. And so we have no choice because we aren't doing all that potential diagram stuff. And so we're going to keep it simple. Okay. That's what's happening with that. But that's an advanced level problem. Once we have the skeleton redox done, we just separate it into half reactions. And so here we separate each half reaction. So we do ethanol goes to CO2. We balance all elements other than hydrogen and oxygen. Balance the oxygens by adding water. Balance the hydrogens by adding H+. Balance the charge by adding electrons. And then add the two half reactions, and we get the net reaction. That's what we do. That's in chapter 5. So here's some examples of skeleton redox reactions. So let me talk about the third type of reaction, which is acid-base reactions. Acid-base reactions all share the same driving force, stronger acid to weaker acid. But we have three types of acid-base reactions: Arrhenius, Bronsted, and Lewis. All we need is one type because Lewis encompasses all acids. Bronsted is a subset of acids. And Arrhenius is pretty much worthless. So we're just going to focus. The reason we don't get rid of Bronsted, even though we could treat everything as Lewis, the reason we keep Bronsted is because it's easy. Lewis is hard. Sure. For Bronsted acids, Bronsted acid is a proton donor, Bronsted base is a proton acceptor. And so the method is very similar. This is the Bronsted method. And that is, we inventory, like redox, we determine the strongest acid and the strongest base present using the chart. And then we transfer a single proton. In redox, we might transfer 1 electron, 2 electrons, 3 electrons, 5 electrons, something like that. So we got to watch out. Here, it's just a single proton. Determine driving force, if any. Stronger acid or weaker acid. And so all we have to do is use the chart, the Bronsted acid chart. So I unfortunately did not put the Bronsted acid chart here. I have the Bronsted acid chart here. Does somebody know how to rotate? I could rotate in Adobe Acrobat, but you know this computer doesn't have Adobe Acrobat installed in here. And so these PDF files all open in Microsoft Edge. Well, sorry. Does somebody know how to rotate in Microsoft Edge? All right, well, anyway, can you see the strongest acid? The strongest acid is HClO4 followed by HI, HBr, HCl. And so here's our acid ranking. So we just rank them, like the strongest acid, weakest acid. There's a conjugate relationship. The bases are over here. Now, there's some nuances. There's some things you need to know about this chart. One of the things you need to know about the chart is this. The chart says which is stronger, HClO4 or HI, HClO4. But there's something called the leveling effect. Have you heard of the leveling effect of strong acids? Yes? Did you guys cover it in Chem 1A? Well, I know, Eric, you did, but what about you other? Does anybody remember? The leveling effect is this. HClO4, HI, HBr, HCl, all these strong acids have the same strength in water, so they're all tied in water. What happens with these acids is this. If we have a strong acid like HClO4 in water, water is the base. So water being the base comes and plucks the proton off. And it turns out plucking the proton off of any of the strong acids is very easy. And so water can pluck that proton off, and usually we write it as an ionization equation like this. You know, HClO4 becomes ionized to H plus and ClO4 minus, right? And H plus, when we think about the composition, what is H plus made out of? A proton. And now the thing about a proton is extremely small. Like a hydrogen atom, do you know how big a hydrogen atom is approximately? Approximately how big is an H atom? Hmm? 200 ppm? Yeah, more like 100 ppm. Yeah, a picometer, about 100 picometers. 100 picometers is the same thing as about 1 angstrom, so about 1 angstrom, or 100 picometers. So an H atom is about 100 picometers. And in the middle of the H atom is the proton, or the nucleus, right? How big is the nucleus? Because if we strip off the electron, then the size of the atom is going to shrink to the size of the nucleus, which is extremely small, like 10,000 times smaller, right? And so the nucleus is tiny, and it has a full positive 1 charge. What can you say about that?
High charge density.
A high charge density. In fact, H plus does not exist. H plus AQ does not exist. Now, I know some people, Chem 1A instructor says H plus AQ doesn't exist, so I want you to write everything as hydronium. That's okay, but I don't have everybody write everything as hydronium, and nor do we see it on the charts. We're just going to use H plus AQ. If we see H plus AQ, it really means H3O plus, because H plus AQ is too reactive to exist stably in water. It's going to immediately react with water. And so one other way of thinking about this is H2O liquid is a base. H2O liquid does this process. Do you know what this process is called? Rather than ionize, it's going to hydrolyze. This is called hydrolysis. And so what happens is this water plucks off the proton. It can pluck off the proton easily to form hydronium. Initially, when we do it, we think this, H plus. But pretty soon, we're going to think in terms of hydronium, soon enough. But right now, we don't have to think in terms of hydronium. Okay? That's hydrolysis. Well, it turns out that all these are so easy that there's no problem. Water comes along, it plucks off the proton. Easy, 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 easy. And then it gets here, and what happens? It becomes more difficult. And so it doesn't pluck it off easily. And then as we go down here, it becomes harder and harder to pluck off the proton. And so for strong acids, there's no problem. 100% of the protons can be plucked off. They're very easy to get. But as the acid becomes weaker, the bond becomes stronger, and it becomes more difficult. And so that means something like this. If I put H2SO4 in water, H2SO4 is a strong acid, right? And so the first proton's easy to pluck off. Very easy to pluck off. And so water comes along and it plucks off the first proton. That was easy. And then the second water comes along, you know? And so let's say your friend comes along, the second water molecule, and comes and says, okay, I'll take the first proton, you can have the second proton. These are like apples on a tree. So I get the first apple, you can take the second apple. But when the second water comes along, is it going to have an easy time plucking this proton off? If it did have an easy time plucking this proton off, then what we'd end up with is 2H plus plus an SO4 2 minus. Both protons, so easy to pluck off, you know, no problem. But do you think that's going to be the case? It's not going to be the case. The first proton is going to be easy to pluck off because this is a strong acid. The second proton is going to fight. So that water is going to come in here and try to pluck it on, but the sulfate's going to say, no, I'm going to fight for it, right? And then there's going to be a little tug of war going on. And so a weak acid does not ionize 100%. Does not hydrolyze 100%. A weak acid, we stay together. And so this is why if you wrote Tuesday, if you wrote 2H plus an SO4 2 minus, I said that's wrong. Both protons don't get plucked off easily. Only the first one gets plucked off easily. The second one, there's a fight. For the leveling effect for the strong acids means all these acids, the proton gets plucked off easily. No problem. Water comes in, plucks it off. So easy, right? When we get to the weak acids, it doesn't happen. And so when you ionize H2SO4, ionize it like this. So let me ask you this. What's a stronger acid? HClO4 in water or HI in water? In water. Which one's a stronger acid? They're the same. Why? Because HClO4 in water yields H plus and ClO4 minus. HI in water yields H plus and I minus. Which one has more H plus? They're the same. Versus acetic acid, does acetic acid, is that proton plucked off easily? No. And so acetic acid is going to have a lot less H plus. And so that's a weak acid. And so we got to worry about the leveling effect of strong acid. And we have to worry about the leveling effect of strong bases. What are the strong bases? The strong bases are hydroxide. I know you have to twist your head for this. Sulfide, amide, oxide, hydride, methide. That's the name of these species here. It's in the chart. Actually, no, I didn't post that chart for that. These bases are too strong to exist in water. The strongest base that can exist in water is hydroxide. So if we have something like hydride, hydride immediately attacks water, plucks a proton off water, and we end up with hydrogen gas and hydroxide. And so all these do something. All these bases do not ionize. Bases hydrolyze. So all these bases hydrolyze water completely. And so these are also leveled, because what happens is all these bases are too powerful to exist in water. They all react with water, and they all produce the same product, hydroxide. So something like this we could do in two ways. Phosphoric acid plus sodium hydroxide. The two approaches we can take are the metathesis approach and the Bronsted approach. If we do this metathesis approach, it's going to be like this: H3PO4 plus sodium hydroxide. And when we do metathesis, we react it all the way. We don't do partial reaction, we just do full reaction. If we do full reaction here, what does it form? If we do full reaction here, it's going to form sodium phosphate and water. And so what we're going to do is we're going to neutralize all three hydrogens using 3 sodium hydroxides, and we'll end up with 3 waters. This is it. Now we look at the driving force here. What is the driving force? The driving force is going from a stronger acid, although this is a weak acid, it's stronger than this. Water would be the weaker acid over here. So we got driving force. This would be the complete equation, then we do the ionic equation, and the net ionic equation, something like this. This would be the metathesis approach. For the Bronsted acid-base approach, we do it different, because this transferred 3 protons. For the Bronsted, we just do it 1 proton at a time. That's the way we do it. I'll show you an example of Bronsted later. These slides, did you do chapter 16 in Chem 1A, the last part of chapter 16? The Lewis structure and acid strength? Lewis structure and base strength? Okay, you should review that. If you didn't do that, you should read through it. The last part of chapter 16. We have chapter 16 in the 1B book too. But this talks about that, you know, the theory. Bronsted acids and bases are fairly easy to understand. Lewis are much more trickier. Lewis acids and bases, we don't have a simple table of acid strength and base strength for Lewis acids and bases, because the strength depends on the combination. And so here's an example of Lewis base ammonia. Here's an example of Lewis acid boron trifluoride. Lewis bases are electron pair donors. Lewis acids are electron pair acceptors. When a Lewis acid and Lewis base react, it forms a covalent bond like this. But this is a covalent bond that the bonding electrons came from one atom, nitrogen. So we call it a coordinate covalent bond or a dative bond. And we form a complex like this, or an adduct, or whatever. And so this is the compound that results from this. We can identify sites of Lewis acidity and Lewis basicity, but basically to understand the strengths, we need to use this, HSAB, or quantum mechanics. HSAB is a simplified version of the quantum mechanics of acid, Lewis acid strength, and Lewis base strength. And it's called hard, soft, acid-base theory. And with HSAB, you don't have to do computer calculations. You can just use tables or do it based on simpler analysis. Okay, but the point is that the Lewis acids and bases aren't so easily ranked. Lewis acid-base reactions are a bit more difficult in predicting. And so let's take a look at a Lewis acid-base reaction here, and then we'll go on break. We're going to look at carbon dioxide, CO2, and water. This is an example of a Lewis acid-base reaction. Carbon dioxide is both a Lewis acid and a Lewis base. And same thing with water. Water is both a Lewis acid and a Lewis base. And the way we figure it out is this. Lewis bases are electron pair donors. Well, I have two oxygens here. Electron pair donors, we want negative charge density there. And these do. These are delta minus, carbon's delta plus. And so we have Lewis base atoms. These Lewis base sites would be this oxygen here and this oxygen here. We also have a Lewis acid site. The Lewis acid site would be the carbon. Now, how can the carbon take another pair of electrons? Because the carbon already has an octet. If the carbon already has an octet and gains another pair of electrons, it's going to have an expanded octet. Can carbon have an expanded octet? Is it possible for carbon to have an expanded octet? No, it's not possible. But if we rearrange the electrons, it is possible. And so let's take a look at that here. This would be our Lewis acid site. For water, this is delta plus, delta plus. Lewis acids are positively charged regions. This is Lewis acid that's capable of accepting a pair. So this is a Lewis acid. Oxygen, this is our Lewis base. It's delta minus and has lone pairs. And so we have two potential reactions that can occur. We can look at reaction one. Reaction one would be like this. Do you guys remember hybridization? What's the hybridization on carbon here? This is sp. What's the hybridization on oxygen? Did you do terminal atoms as hybridized or unhybridized? I hybridize. And so if I hybridize the oxygen here, what is the hybridization? sp2. So that means this lone pair is in an sp2 orbital here. And this sp2 lone pair if this sp2 lone pair gets pushed into this, now I'm going to use valence bond theory. Valence bond theory says a bond is what? Did you guys have an opportunity to review the bond theories? Valence bond, MO? No? Okay. Valence bond says that a bond is the overlap of atomic orbitals. So what type of bond is this? This is going to be an S. And what's the hybridization on oxygen? Joanna, you know that one? sp3. This is going to be an S-sp3 sigma bond, right? And so the sp2 electrons get pushed into the S, and it's going to kick out the S-sp3s and put them in the sp3 orbital on oxygen. That's one possibility. And so this is reaction possibility one. Reaction possibility two goes like this. Reaction possibility two is we'll take this. This lone pair is in what orbital here? sp3. This sp3 lone pair gets pushed. It's going to get pushed into p orbital here, but there's already a pb pi bond here. That pb pi bond is going to break and give these electrons to oxygen. That way we can accommodate another pair of electrons. This is reaction path 2. And so we have path 1 and path 2. We try them both out because, when we're going through the jungle, we'll try all the paths out to see where they lead. Maybe they'll lead to our whatever, or wherever we're going. Maybe they won't. But I don't have enough time to go down the wrong path. And so I'm going to skip the wrong path. We're just going to go down the right path. The right path is going to be 2. If we went down the wrong path, we'd end up at a dead end. And so we take reaction path 2, what happens? When we go with reaction path 2, then nothing happens over here. We got this double bonded, but now we got this water bonded up here. It's stuck on here. So we got this water like this. And this is going to convert to a single bond, like this with a lone pair. And so we have this Lewis structure. When you look at the Lewis structure, does it look good to you? No, it doesn't look so good. What's wrong with it? Does it violate the octet rule? Does this Lewis structure violate the octet rule? It actually, you know what? It does not violate the octet rule. So if it doesn't violate the octet rule or the Duvet rule, what's wrong with it? The formal charges. The formal charge is all screwed up. What's the formal charge on this oxygen? +1. What's the formal charge on this oxygen? -1. So one oxygen gained an electron, the other one lost. If there's a tug of war, oxygen versus oxygen, does one oxygen gain, the other loses? No, it's not stable. This is not stable, right? This is not stable. This is an example of an intermolecular reaction. Have you ever heard of an intramolecular reaction? What's an intramolecular reaction? An intramolecular reaction versus an intermolecular reaction. Intra means within, inter means between. And so intermolecular reaction is between two molecules. Intramolecular reaction is within the same molecule. Within the same molecule, what would you call this oxygen? Lewis acid or Lewis base? Lewis base. What would this hydrogen be? Lewis acid. We got a Lewis acid, Lewis base right there. What can happen is there's motion. At room temperature, what are the three types of kinetic energy? What are the three types of motion? Rotational, translational, and vibrational. And so what we got vibrations. So imagine this. Imagine a pretty intense vibration occurs. And this vibration does this. It pushes this sp3 lone pair into the s and kicks out these the s-sp3 bonding electrons into the sp3 orbital here. If we do that, then what we end up with is this. We end up with this molecule. Do you recognize this molecule? Do you recognize? What if I wrote it like this? I'm going to write it as H2CO3. Do you recognize that molecule? H2CO3? That's called carbonic acid. Carbonic acid is not stable. Carbonic acid decomposes into CO2 and water, so there's no driving force for this. It should be CO2 and water. Carbonic acid is unstable. It should be, but do you know what equilibrium is all about? This is what equilibrium is all about. Can you stop waters from colliding with CO2? Can you say don't collide? Can you do that? No, the waters are going to collide with the CO2 regardless of whether you tell it to or not. You can't stop it. And what's going to happen is, no matter what, these are going to collide, and eventually some of those collisions are going to lead to carbonic acid. The carbonic acid is not going to live very long. It's going to quickly decompose. But what's going to happen is it's going to reform. And pretty soon, you know, this decomposition and this reforming rate are equal, and we reach a state of what's called dynamic equilibrium, and we have a little bit of carbonic acid always present, even though it's always decomposing and reforming. That little bit of carbonic acid that's always present contaminates our DI water. Do you know what the pH of our DI water is? The pH of our DI water is 4.5 to 5.5. Is that pure? No, pure water should have a pH of 7. And the reason our DI water is so acidic is because it's stored up in the tank up here, and that tank is filled with air, and that air contains carbon dioxide, and you can't prevent carbon dioxide from colliding with water to form a little bit of carbonic acid. And so we got to worry about this. This is an example of a Lewis acid-base reaction. Lewis acid-base reaction is much more involved than Bronsted. So this is why we keep Bronsted, because Bronsted are so simple. If you had to do all reactions like Lewis, it'd be kind of a pain. And so we don't do that. All right, that's pretty much it for the... we'll take a break. Let's take a break for 15 minutes or so. We'll start again. 341 or so, 342. Are Lewis acids and bases going to be on the test? Actually, this you know. Because of the widely varying, you know, this is all review for some students, or this is all new for some students. Because of the widely varying instructor preferences in Chem 1A, I give a lot of extra time for this. So I'm not going to test you on this for a while. We're going to be working with so many chemical reactions and equilibrium calculations that you should start building up the skills to do this as we go along. And so you're going to get tested on this on the final exam. I'm going to test you on chemical reactions, but maybe I should test you before then. So, but it's not going to be so quick. Okay. So, or maybe I don't know. How do you guys feel? Did you start the homework? The homework's posted on Piazza. That's actually the same homework I gave in Chem 1A, but it's all posted on Piazza. See how you feel. Maybe we can have a test on it sooner. But we'll see, because we're going to continue on the worksheet. So let's start again at 3:45. And